Okay, welcome to the next panel. I'm not going to introduce the speakers individually. I let them do it themselves. We are running a little short of time. So first we'll go Li Hao Chu, then Wentao Huang, Paul Siegel, and finally I will close the session. Okay.
My name is Wentao. I was a PhD student at Caltech during 2011 and 2017. Shuki was my advisor. And today I'm going to talk about some work that we did during this time. Just secret sharing schemes from the coding perspective. I will get a little technical, but don't worry, we'll keep it simple and short. So a secret sharing scheme you can think of is just a secure erasure code. Right? So we have N nodes, we want to be resilient to R failures, and Z eavesdroppers, which means we have, if Z of the nodes are wiretapped, we don't lose information to them. So Shamir was the first one who started these schemes back in the '79, and over the years it was very, very extensively studied in the cryptography community because it's a very important building blocks that can be used to build many other crypto protocols. But in the views of our coding community, it's just an erasure code with security, except that it is very inefficient. So I will show you why by a very simple example. So here we have a secret sharing schemes that can deal with one erasure and one eavesdropper. It is super simple. We have two message bits, M1 and M2. We have one random bit U. I call it a key because it's used for security purpose, like for one-time pad. And then it is very simple to encode. Just two XORs to encode a bit, and one XOR to decode a message bit. In fact, we show this is as simple as you can get. You cannot do better than this because the encoding matrix has to be dense enough. So now this scheme looks good, right? It's simple. It's kind of schemes that will work in the real world, except we don't know how to generalize it to R and Z greater than 1. We don't know how to generalize it to deal with more than one erasure or one eavesdropper. So yes, there are hundreds of secret sharing schemes out there, but none of them are even close to this one in terms of simplicity and computational efficiency. So we started our journey with a very simple question, right? For the first non-trivial case, R equals 2 and Z equals 2, can we construct a scheme that is as simple as the previous one, like with optimal computation complexity? And well, we are able to find that scheme. It's like this. This scheme is optimal. For example, we can observe that every message bit is padded by exactly 2 key bits, and you kind of have to do that because you need to pad by 2 keys in order to defeat 2 adversaries. I will just very quickly go through some of the ideas behind these schemes. It looks very simple, but there are some deep theory behind it. Right, so it is a combination of 2 code, one erasure code and one secrecy code. First, we are going to pick an optimal code. Optimal code is erasure code, like the even OR code. And then we are going to use deal code as the secrecy code. And this code tells us how to pad the key bits to the message bits. And then this doesn't work automatically because these 2 codes can fight with each other. Like one can break the erasure code can break the security of the secrecy code. Right? So we did some more conditions to make sure they are kind of compatible. And that is to the secrecy code must be a subcode of the erasure code. Right? And that usually doesn't work for the deal code, but usually you can modify the deal code a little bit to meet this condition. So this idea turns out to be quite successful, quite powerful. We're able to apply it to, like, for almost every family of code that we try on. It kind of works. Even not code, B code, RDB code, start code, as well as a family of array codes over the RP ring. So together, this gives us many families of code that are very, very simple, with optimal encoding and decoding complexities, and with very flexible parameters. I should thank Shuki for introducing me to this amazing array code. One last thing I want to talk about this work is that I think reflects, and this is a recurring thing in this seminar, it reflects how Shuki values simplicity and the power of it. Right? So if you look at this scheme, it's so simple that it makes you wonder, how is it possible that nobody discovered it in the 50 years since secret sharing scheme has been existed, like after tens of thousands of papers? So I think that speaks to like how unique Shuki is, how the strength of the principle of simplicity, and also like finding simple solutions takes hard work. Thank you.
Hi, everybody. It's great to be here to celebrate Shuki. I'm Paul Siegel. I'm a professor at the University of California, San Diego. I work at the Center for Memory and Recording Research, and my research group is the Signal Transmission and Recording Group, or the STAR Group, also known as the Flock of Seagulls. So I've had the good fortune that my career and my life have been interwoven with Shuki's for almost 40 years now. We both started at IBM Almaden, had a great time there, and then we transitioned to academia at about the same time, Shuki in '94 and myself in '95. I think it's fair to say we both love the academic life, and we've stayed where we landed. Shuki and I have a lot of research interests in common, and that's been very nice because we've been able to continue interacting closely, really, for all of that period of time. We share many wonderful mutual colleagues and friends, which includes our students, our postdocs, and these days, Shuki, even some of their students. We've traveled the world together, had a lot of laughs. I love Shuki's sense of humor. And we even have some family birthdays in common. This is where it all began. This is the letter that was sent to Shuki when he was a graduate student at Stanford, inviting him to join the signal processing and coding project at the Almaden Research Center in San Jose for a period of 12 weeks. Shuki, do you see what your salary was? That was the start of your lucrative career in engineering. We really wanted you to come, so. Shuki and I attended the ISIT in 1988 in Kobe, Japan. I'd like to think that nothing much has changed about us in that time, but I think, honestly speaking, the only thing that hasn't is your smile. We also attended the ISIT in Whistler, British Columbia in 1995. We joined a group of people who climbed up, went on a hike up a small peak. Shuki sent me this photograph, and there was a Post-it note on the back that said, "It was fun up there, Shuki." And I still have the picture and the Post-it note, and that just proves, Shuki, that paper is one of the most durable storage devices that we have. So now I'm going to fast forward to 2011 and the second annual Non-Volatile Memories Workshop that was held in La Jolla, California. The first workshop was really a trial balloon. We didn't know how many people would show up, but the turnout was pretty good, and we really expected a big audience at the second one. And we knew we had to have a sterling keynote speaker. And Shuki really had, I would say, set the academic world on fire with his work, his pioneering work on information theory and coding theory for flash memory. So we knew that he was the man to get, and he very graciously agreed to come and speak. He spoke, as you can see, about rank modulation for flash memories, which is a very innovative concept that originated in his lab in work with Andrew Jang and others. And you can actually still find the video of his presentation on YouTube. So I encourage all of you to check it out. It's a great talk. Lots of Comic Sans font and little cartoon characters. Okay, now I'm going to jump ahead to 2023. The editors of a special issue of the IEEE Bits magazine were putting together a set of articles on information theory and data storage. And we knew that we had to have something about coding for DNA storage, DNA-based storage. And once again, Shuki and his group had really paved the way in this area. And we really wanted to get an article from him, and we were lucky enough to do so. The article was written by Shuki and by Jin and by Netanel, and it's really a masterpiece of exposition. I encourage all of you to read it. It's really fantastic. Okay, most recently, we had a star group reunion, which included many friends and colleagues. And it really would not have been a reunion without Shuki being there. So it was great to have you there, Shuki. We're very glad you could come. So congratulations, Shuki. Thank you for 38 years of friendship and fun. And I hope you continue to have fun up there.
Well, okay, I think I go next. I don't know how, Paul was my manager at the time when he sent that invitation to Shuki. The interesting thing is that would change my life also. But perhaps I'll make some comments on that tonight. Let's go now. We're running a little behind. I want to talk a little about the origins of the even-out code that Yasser mentioned this morning and went out now. I added Shuki as a co-author, probably reluctantly here, but you have no choice. So this is Shuki at the time. It was early 90s. We were at IBM. I was in storage. Shuki was at computer science. But we used to work a lot together. And Shuki one day comes with a problem. We had array codes. For instance, the first 5 columns in each of these arrays carry data, and we want to add 2 parity columns. But the problem we had at that time, I didn't have a problem, but Shuki brought it. People in computer science as well, if we want to update a symbol, we have to update the 2 parity columns. So we want to minimize that. So we came up with the following code. Let's put parity on rows. We have 2 column parities. And the first column parity carries, the one in red, horizontal parity. And the second column, you see the one in blue, these are wraparound columns, carry also even parity. The last row here is imaginary. It consists of zeros. I put the last row just to, you can follow the direction of the diagonals, but the last row doesn't exist really. So we have even parity on rows and diagonals, and this code in principle can correct any 2 erased columns. So this is what happens. We want to update a symbol, the one in red, that is a 0. So we update the horizontal parity and the diagonal parity in the second column. So we update only 2 symbols. There is a special diagonal at the end that we don't update at all because we cannot update the last column at the end. I said it's imaginary. So we wrote what is called the disclosure. We sent it to the legal team to be analyzed and probably patented, and we went home very full of ourselves. We had solved the problem. Great. Here is another example. We update the symbol in blue. We update 2 other symbols. So Shuki calls me that night and he says, we have a problem. Houston, we have a problem. When Shuki says we have a problem, we have a problem. I started sweating since that moment. I knew something bad was happening. And he says, look at the special diagonal. And at that moment, I realized, immediately I understood what was wrong. I don't want to hear it, but this is what went wrong. It is what it is. I update the special diagonal, so the only symbol I can update is in the horizontal parity. The diagonal parity I don't update. But what happens here? Imagine that the two columns containing the two ones in red are gone. So we have two possible decodings in this case. The old zero array and the one here. We have two solutions. The code is not MDS. Total disaster. I got desperate at that moment. I started thinking all kind of nonsense as usual, but nothing worked. But 24 hours later, we solved it. And what we had to do is in the special diagonal, if I update a symbol, I have to update all the symbols in the second parity. And that solves the problem. I'm not going to go into proofs of that. But one effect of that is that the diagonals now have either even or odd parity. In this case, all the diagonals have odd parity. Look at this one in blue. You follow the diagonal. I have only one. I have odd parity. And all the diagonals have odd parity. And that parity is determined by the special diagonal. And we solve the problem there. Eventually, and this takes years, this was early 90s. In the mid-90s, finally, the paper was published, the even odd paper. A funny thing happened. It was accepted, no problem. But one of the reviewers said, why did you consider even or odd parities? Just to give a catchy name to the code, even odd. Is it true? Okay, we didn't answer to that. The paper had been accepted. And, oops. And the last time I checked in Google Scholar, it has been cited nearly 1,000 times. Certainly this is not true for Shuki, but it's a record for me. Conclusions, we are running out of time, but even if we had time, they are unclear to me. I could tell you lots of nonsense, but I'll give you one conclusion. Every time I run into trouble, I have a friend that bails me out, and that's Shuki, and I thank him for that.
Thank you, Mario. I learned from him about, he gave me support for my view of kindness, because it's true that I was paid $680 a week. But when I came to work in Paul's group, and Mario was my mentor, he said, we will sit in my office. It's a very small office. Basically, we were sitting next to each other in his office the whole summer. And he taught me about coding theory. I never will forget that, Mario. Thank you.
And that summer was a lot of fun.
Yeah.
It was not an effort.
Mm-hmm.
I'm Bella Bose. I'm from Oregon State University. I'm a professor there. I met Shuki. I spent my sabbatical at Stanford in 1987. That time, Shuki was a student. One of my friends introduced me to Shuki. That's the first time I met him. And then I think he joined IBM. and Shuki and Mario and Paul, they invited me to give a talk. I've known them for a long time, okay. And okay. I work in coding theory area. My work is influenced by the last 15 years, influenced by two important papers. These are the two important papers. And codes for asymmetric and magnitude error correcting with application to multi-flash memories. And you can see all the authors here, Shuki and his students. Other second paper is rank modulation for flash memories. These two papers were, they were awarded best paper awards. Okay. And to just give you an idea, flash memories, I am taking the slides from Shuki's group, and this is Andrew's slides. This is what Shuki introduced. Okay, when I read the paper, that's what I understood. So you have a flash memories, single cell. If you have a cell, you can store only one bit, either 0 or 1. And that time, so they wanted to increase the density of the flash memories. So in each cell, they can store up to 4 or 8 bits per cell. Okay, and one of the problem is writing the cells is very difficult. So you can program it from lower level to a higher level, you can easily go. But once you go to higher level, in order to come to the lower level, you have to erase about tens and thousands of cells, go back to 0, and again you rewrite it. Okay. In order to avoid that, they do it very slowly, about 8 or 9. Okay, if you want to come to up to there, so slowly they program it, and it comes to about 8 or 9 times you have to do it. It takes quite a lot of time. Okay, so you don't want to overwrite on top of a cell. Now, other important thing introduced here is this is very important from our research point of view. So the most of the errors in memory cells are of asymmetric type. Okay. So in the Warshme introduced long time ago, the asymmetric error is, it may go from one level to the other level. Say if you're in the level 3, it can go to 2 or 1 or 0, but not necessarily from the lower level to higher level. But what Shuki and his group introduced was limited magnitude. Okay, so the limited magnitude error. So what it means here is, if you are in one particular level, it may go to next level. Okay, or most of the time it's asymmetric error. Okay, or it may go to one level higher. Okay, so this is one of the areas I used to work, and when I read here, I got very much interested in this area. So for the last 10 or 15 years, we have been working here. Very thanks to Shuki and his group introduced here. When I look at all my papers in the last 15 years, these are the papers. All are based on Shuki and his group's results. And this one and the other one, almost these are my journal papers. So important thing is, because of this one, I was able to get NSF grants. If you look at here, 4 or 5 grants, all of them are based on Shuki and his group's result. NSF thinks we are doing good work, that's why they are giving us work. Credit goes to Shuki and his group. And what we are doing here is, just to give you an idea, the type of work we are doing here is based on elementary symmetric functions. I don't want to go in detail about all these things. So instead of looking at a power sum series, we are using the elementary symmetry functions. That gives much better results. One other important result is Shannon introduced 1956 zero error capacity channel. And because of Shuki and his group, we thought about it, and we came up some interesting code. It achieved the zero error capacity. Again, thank you again, Shuki, and a wonderful and retirement life. Enjoy your life. Thanks again for all your contribution to not only field and as a human being, as a friend. Thanks again.
Okay. We go into questions, or we start with the next session. Any questions, comments, nice comments, bad comments?
Let me just add one thing you probably remember now. When I interviewed at IBM in 99, you were the host and you showed me your office, and on the office door, there was Shuki's name on that.
Ah, yes.
Long after Shuki left.
Yes.
Yeah.
I couldn't stomach very much that Shuki had left.
Yeah.
We had a name. I always kept Shuki's name in my office.
Yeah.
For,
Number one, it was job security for him. And number two, he kept getting the $680 a week. I'll talk about it in my concluding remarks, but it was a very easy decision. When I joined Paul and Mario group, it was the best group in coding and signal processing in the world. Every summer there was a workshop there. People came from all over the world. Brian Marcus is here. He is a world leader in constrained sequences. He was in this group. Mario. Okay, Mario is okay. Paul Siegel. Mario organized this workshop. People came, like Golom and Jack Wolf and many other people that started this whole area. The same was true in computer science. When I joined computer science, on one side, my neighbor was Nimrod Megiddo, that is very famous person, and is still active. And the other side was Miki Aitai, that is a fantastic mathematician, and so on and so forth, Pippinger and Larry Stockmeyer, and I was walking the corridor and trying to walk slowly and quietly. So both on the coding and computer science, there were fantastic people. The same was true at Bell Labs. And then something not good happened. And most of us left, including Paul and Brian.
When Shuki told me that he had an offer from Caltech, it was a complex decision for him, and not only for technical reasons, his family, his friends, and what I told him, it really pained me, but I said, I am a Caltech graduate. I said, go to Caltech. It's the best place in the world. It's incredible talent, and I rest my case.